그러면 뭔가 지금
Shut the fuck up!
So already we are going into assignment 3 this week. So I'm going to go over the given code basically and try to explain to you what's important and what you need to do. Has anyone read the assignment 3 description?
Nope.
Okay. Did you guys have a midterm already?
No.
It's pretty easy. So actually this is not that much. So I think it's okay that you can do it. So has anyone know what VM is? Okay. So basically that's the VM that we had until assignment 2. It basically just allocating memory continuously. And it didn't do any paging or any smart memory management. So your goal is getting rid of VM and trying to implement paging. And also swapping. So actually you'll be able to run user program requiring more memory than the RAM that you have. So, fortunately for you, assignment 3, you need to only implement these 3 functions. Most of the structure is already given in the code. And there's an instruction how to pull the assignment 3 starting code, and also you can use assignment 2, and it tells you how to add assignment 3 code on top of yours. Or you can choose to start fresh with the assignment 3 code. Basically, to explain, this function handles page fault. So when you're trying to access the memory that's not in the memory, you bring it from the disk and load it to memory. And page evict is evicting a page to disk. And when you run out of memory, and page replace is basically how you select the which page to evict. And there are 2 versions you have to implement. On assignment says to implement sequential page replacement first and then try random. I think you have to finish both of them for assignment 3. So starting code, there are a few additions in the VM directory. Please make sure you read the code. Yeah?
So this is a free one. So you could start with either our assignment 2 or fresh copy, right?
Yeah.
For assignment 3, the link will from you. Is the previous code already done?
No. So that's the thing. It's not done. And they're not needed for assignment 3.
Okay.
So for example, the argument, like when you run the virtual program, you implement it like passing argument, right? That's not done.
Okay.
But it's not needed. Okay. Yeah. I'm going to talk about the memory management unit after this. So, did you guys cover MMU before in the lecture? Yeah. Okay. So it's all in the hardware, and there is a TLB, which is like a cache of the page table. In MIPS, there's 64 entries, and it's fixed. We can't change it. And how to manage this TLB is all done in software for OS 161. And there are functions already provided for you. Basically, what TLB does is that when you're translating virtual memory to physical, if it's already in the TLB, you can just skip looking into the page table and just use the physical memory address there. If it's not in the TLB, you will track into OS and you have to basically look for the translation from the page table and update the TLB, and then retry again. This is just the description of the memory structure. Like memory size is 4 kilobyte page size, and 64 entries TLB. 12 bits because page size is 4 kilobytes, so you need to have 12 bits offset. Yeah, and TLB is 64 bits instead of 32 because you need to store the virtual address, but also you need to store the other flash bits. For example, if it's valid, or if it's already written, dirty, or if it's global, etc. So we use two 32 bits combined. So first one is called entry high, and the second one is entry low, and it's by pair. So this is how it looks like. So this is entry high, and that's entry low, and this stores the virtual page, and that's the physical page address. And this is 20 bits and 12 bits and 20 bits and 12 bits. Since they're left over here, we use this to store the flag. And here are 4 flags. 30 means it's writable memory. D means it's valid, so it's the page is in the memory. Non-cache, I don't think you'll use it, and global is for the for all the processes. Any questions?
Valid meaning you can write it, or is it?
Valid means it's in the memory. It's valid. So you can just like use the physical address there. If it's not valid, it means you have to load it from this. The 30 means it's writable memory. It's not read-only. So if it's not set, it's read-only. So if you're trying to write to the memory, you will fall into the trap, and you have to handle the exception.
Do we load the memory?
Sorry?
The global one, does the OS does it for us, or do you need to remember?
I don't think we'll use it for that. But it's for all the processes. So for example, like you don't need to delete this when you're changing process. For example. So if it's not set, you have to flush TLB when you change to other process because your address space changes. But if global is set, it means it's for all processes. You don't need to change anything. But it's not used for this assignment. Any more questions? Pretty clear? So, and then, do anyone know why it's 20 bits? So, I think it's review, but so one word is 32 bits, right? And you need 12 bits for offset. So basically, you need to know. So each page is 4 kilobyte, and you need to know where in 4 kilobyte you're accessing memory. So you need this offset because 2 to the 12 is 4 kilobyte. So leftover 20 bits is used for index of the pages in the page table. So there are 3 exceptions related to TLB in NIPS trap. If you look into NIPS trap code again, I think I can show you. here, after checking system calls here, if it's not system call, you check if it's memory exception from TLB. And there are three cases. One is you're trying to write to read-only memory. This is you're trying to read memory that's not actually in the memory, and you're trying to write to memory that's not in the memory. So, okay, just to make it clear, these are the addresses, and you're trying to either write or read to the address. But the memory, if the memory actually is not in the actual memory, but it's on the disk or somewhere else, then you will fault here, and you have to handle. So, for example, if it's not in the memory, you have to load it from the disk and put it into the memory. If the memory is full, you have to evict some other memory to put it into the swap disk, stuff like that. Okay. Any questions? So this is how the exceptions happen. As you saw before in the mixed trap, all these three cases you call BM fault, which is the error function for the memory related. And here you get the address space of the current thread, and you call the address space specific memory fault function. And you're passing the what kind of fault it is. For example, read-only error, read error, write error, and then the address that you were trying to access. And in here, you check if it's valid address, like if it's the address in the address space for the thread. If it is, then you call this function, and this function you have to implement. Basically what it does is it checks if it's in the memory. If it's not in the memory, you load it from the disk. Any questions? Have you covered swapping? No? So basically you have limited memory in your computer, right? And if you're trying to use too much memory, like more memory than what your computer has, you need to evict some memory in the pages so that you have a free space for your memory you're trying to use. And how you do it is, because disk is much larger on storage, you store the memory page that you don't need at the moment into the disk so that you can load the page that you want right now, the memory that you want to access. And then, since you store that into the disk, when you need it much later, when you actually need it, then you can go to the disk and grab it. But while you're doing that, if it's full again, you need to evict some other memory, make a free space, put it into the disk again, and you load it from the disk. So, like, disk I/O is much expensive than the memory. It takes lots of time. That's why you're learning page eviction algorithms like FIFO or LRU, stuff like that, to predict which page you don't need as much as possible, so you want to avoid this swapping. Questions? Yeah.
So the mechanism still works because you have 100 megabytes of memory, the program needs 200 megabytes.
Yeah, because that's why you divide into pages, because you don't need all 100 megabyte at the same time. So whenever you're trying to For example, if you're trying to read the data and that page is not in the memory, you just load page by page. So like, yeah, you can do that. More questions? Okay. So in the mix, page table is not controlled by hardware. In Intel it is. So in Intel architecture, page table structure is fixed. But in mix, you can do whatever you want. So in OS 161, you have separate page table structure, and it is the VM object. I'm going to show you how it looks like here. So it has an array of L page. L page is for our logical page. I'm going to describe to you again, but it's actual physical page addresses. And this is the starting virtual memory address. And that's the red zone. I'm going to talk in a moment. So what it looks like is it has a virtual address, and there are multiple pages like this. These are all virtual addresses, and each of them is mapped to a struct called L page. And this is includes a physical address. So basically, this VM object has multiple virtual addresses, and then there's a link to physical address. So it's kind of virtual to physical mapping. So it's a form of physical page table. One thing to note is this is contiguous. So if, for example, if this is memory 800, it will be, I don't know, like this. It's contiguous, but actual physical address can be anything. It doesn't need to be contiguous. You have this red zone. It accepts the size of the red zone. What it does is, if this is the user stack, you put it under the stack. Divide some memory space where this is not touched, this is not modified. So you kind of protect it from the other address spaces. Like, you're not supposed to go over this. And in other architecture like AMD, this is used as optimization as well. But I don't think it's the case for you. I think it's to avoid overlapping address spaces and detect any errors. Questions? There is a diagram describing this here. Okay, here, actually. This is the address space, and address space has a bunch of the VM objects. In this case, 3 VM objects. And as I told you, this base points to the base virtual address. So this VM object points to coding section. This VM object points to initialize data. And this VM object points to user stack. So the memory space, according to this section, it's divided into separate VM objects. And for each page of this section, there is corresponding L pages, which tells actual physical address. So this is all of these are virtual addresses, and this, for each of these, the pages here, this L page structure includes the physical memory address, so you know how to translate virtual memory to the physical memory address. Questions? So this is the L page. So as I told you, it includes the physical address of the page. Also, it includes the swap address. This is needed if, for example, if you need to evict this page to the disk, you need the address where to evict this page to. So this is the address in the swap file like this. And that's the actual physical memory address. And you need to lock it because multiple processes can access this page at the same time. And this physical address, it looks like this. There's a frame number. You know what frame number is? So for the tables, you don't store all 32-bit address in the table. You only store the 20 bits. And that's the frame number. So it's like frame number 1, 2, 3, and so on. And then you add this 12-bit at the end. That's how you figure out where in the page you are trying to access. So this is only 20-bit, and it's 20-bit of the, if this is the virtual address, this is the page number, offset, and corresponding physical page, physical memory address, you call it frame number, and then offset. You only store first these two, page number and frame number. They are same except you call its frame number for the physical address, and you call page number for virtual address. This is to save memory here. If you want to store the 32-bit, you have to store for every single memory address. But if you only store the first 20 bits and you can figure out the offset later, you save a lot of space. Basically, you save 2 to the 12 bytes. Since they are left over, you use this area as a flag, as a place to store flag. You just set it if it's been modified. So when you're evicting this L page, you first check if 30-bit is set. If it's set, it means this page has been modified. So you need to store what's been modified. If this is not set, and if this is already in the file, you don't need to write to disk again because it's already in the disk and it hasn't been modified. So what's in the disk is the up-to-date version. All lost. Questions? Am I going too fast? mean not here. Yeah.
Wait, in the physical memory it's offset, but some of it is saved for flags. Some spaces for flags.
Not for the offset, but this is not used as offset. In this physical address, you're only interested in which of the frame corresponds to the page. So you only need to store 20 bit because this is like 20 bits. So you have 12 bits left over, and you just use 1 bit there for this 30 bit.
But in the diagram you have there, offset is right next to frame number.
Right. This offset is actually, so for example, if you want to access this memory, right, this is the offset. You only search for this. If you find it from the which physical frame it is by looking at this, for example, let's say this is 8,000, right? Then you found it, and then your offset is 100. So you look at the 100 offset here, then you know where in the page you're interested in. So you don't need to store offset into the table because you know the offset. It's from the memory address. Clear? Like, any more questions? You distinguish if it's not in the memory by this invalid key adder macro. So if when you are looking at the out page, if this is sent to that invalid key adder, it means it's not in the memory. So you likely need to use this swap address to load it from the disk to the memory. And invalid swap adder, if the swap has not been allocated, but usually it will be allocated when you create the node page. So yeah, same as just as I told you before. Since we have this 12 bits left over, we use the last bit to save this 30 bit. So make sure you check this bit, and if it's set, you need to save it to the disk. Otherwise, for optimization, you may not need to. And these are the all the functions related to the logical page. They are all implemented for you, I think. Questions on this? So that's the function you need to implement. As I told you, you need to read a page from the disk for this function. And this is called when you are trying to access a memory address that's not in the physical memory. And out page evict, it's the other way. When the memory is full, you need to evict the page to the disk so that you will have up-to-date information. And as I told you, you need to check if the dirty bit is set. If the dirty bit is set, you need to write to the swap adder. That's the field of the cell page here. Questions? This is a new structure that's used for swapping. And it's the other way from the page table. It's a mapping from physical address to the logical address. instead of the virtual address to physical address. Just helps you which page to edit. So you'll likely use this format a lot when you're writing to disk or reading from the disk. And it's very convenient. I'll show you. This is how it looks like. It has the array of L pages and has the bunch of this bits. Anyone know what this is? Like colon and the number. So it's a bit field. It's convenient because if you do colon 1, it means this variable is 1 bit only. So whatever you store here will get interpreted as 1 bit. And this is interpreted as 5 bits. So if you know how large your data is, and so for example, if there's certain structure, yeah.
Sorry, if you use something larger than 1 bit in something like CM allocator, would a clobbered CM not last?
If you store something large, will it overflow?
Yeah.
No.
No, it won't. It will automatically just get the last few digits of.
No.
No.
It will be something weird, like something negative number or whatever. Like it will be 1 bit, but basically it will truncate all the not used bits,
Right.
and then it will just take the last one. But it won't. It may not be what you want.
Oh. So if I do something like 3, it's not going to set. If I assign 3 to CM kernel, it would not assign like 1 to it.
Then it will just like delete this and take 1.
Oh, okay.
But you have to. I read yesterday, because if you like choose complement, right? So the leftmost bit could be negative, used to note the negative sign as well, right? So sometimes you may get the negative values if you're not careful, and basically it will only overflow for this variable, but the value may not be what you want.
Okay.
This is the TLB index, CPU number, if it's from the kernel or not, if it's contiguously allocated, and if it's actually allocated or not. And this pin is used a lot in the code. Basically what it means is it means that something is changing in this physical memory. Notice this is entry, so if this is the format, every entry here looks like that. So every entry has those fields here. So this is only for one physical page. So I told you format is used for depicting a page. So you look at the format and see if so this is physical address. You look at it if any of the entry is free or not. The way you check it is if this pointer is null, that means it's not allocated, so it's free. But if it contains some L page, it means it's allocated. So you look at the free pages when you're allocating a new memory, and if you cannot find any, if all the entries are full, you need to choose one and write to disk. And you can use page eviction algorithms for that. And once you choose the which page to evict, in this case the last page, there's already functions for that, do evict and the L page evict. And this is the last function you need to write for this assignment. So there are only 3 functions you need to write. Basically, what this does is, I think it's actually, four functions. This is for choosing the victim. Yeah, and actually this is right to this step.
I'm just wondering, when you evict, say, you just pick the last one from the list? Or
No, like
mechanism?
Yeah, like have you learned the basic eviction algorithms, like FIFO, shortest jump first or something like that? Okay, so you use those, but for this assignment, I think it's sequential. So you look, find the first page that's weak and just use that.
I mean, the other way around, when you're evicting, like, one thing's putting them in, but when you evict them, how do you delete those by, if we need to randomly evict the page, do we evict an unpopular page, or like one
That's the algorithm. You need.
you know what?
Yeah, I know what you're saying. Yes.
This first name will be the first name. So you just choose it.
Yeah, like you can be smart about it. I don't think assignment is very clear which algorithm to use. But one thing for sure is for the random eviction, you will randomly choose. But for the sequential one, I think you will use some algorithm. I'm not sure which one. We likely
Cell shading.
Fortunately, you don't need to worry about writing to this actual physical mechanism for writing to this because it's in this swap.c file. So mostly, a lot of things are done for you in this assignment. And if you read the assignment description, it says this is more for you to read the code and understand how it's implemented rather than implementing big part of the assignment. But I think you need to read carefully to understand. So here are some questions. How do you get physical frame from the format? Basically, this is indexed. So if it's 1, it's frame 1, frame 2, 3, 4, 5. So you can just treat it as an array and use index to get the physical frames. Yeah, that's easy. How do you swap page in and out? You use these two functions. They are in the swap.c file, and it does actually write to disk and reading from the disk. How do you know a page has been changed? Yeah. It says if you don't know, you can always write to the disk. It will be slower because you're mainly doing unnecessary work, but you will avoid any errors. So you can do that. If you want to be smart, you can combine read-only bit and dirty flag in a way that if a memory page is modified you will always set the 30-bit. You can combine these two and figure out. How do you map it to TLB? There are TLB functions already implemented. And as I think it's in the format, let's see. You need to find the function from here and call it to map it to TLB. Okay, this is how everything is related. This is the format entry. One entry has logical page, which could be one of the pages in the VM object. So first, this is the address space. So it's all the memory address for this thread, and it's divided into VM objects. And it has a physical page address for each of the pages. And each of this physical page could be linked to this format. Each format entry has the logical page link, and it has other information about TLB and others. And this logical page has the physical address, and this physical address points to actual memory. So we use this to go from virtual memory to the physical memory, and this is the other way around. This is the so this index is the physical frame. Like index is the frame, which is same as the first 20 bits of the physical address. And so you go from physical page to logical page to physical page. So it's like physical to virtual and virtual to physical. You use this to choose a page to evict, and this is for transmitting virtual to physical address. Finally, we need to use spin lock in this assignment. Anyone know spin lock? Yeah. The reason for using spin lock is that you don't want to sleep when you're locking, because this memory, for example, swapping is very expensive. It's like million cycles, so you don't want to sleep while doing that, so you use spin lock. And these are the functions that uses the spin locks. If you remember, each L page has a spin lock. So if you want to access a certain L page, you have to lock it first and use those functions to do that. This pinning means whenever you're changing the page, if you look at the code, it will set the pin bit here, and it will tell you that something is being changed from the memory, so others won't change it. Others will wait until that bit is clear, then we'll try to do something again. There are a few locks already there. Global paging lock. So this is held for any paging activities. And if you want to access this swap file, so swap file is where you store the memory. So when you're evicting a page, you write to disk, which is swap file. So when you're writing to disk or reading from the disk, you have to hold the lock there again. If you're using format, there is another lock, and since there are so many locks, there could be deadlocks if you're not careful. And this guide tells you the ordering of the locks. So one way to avoid the deadlock is if you always lock in same order, then there won't be any deadlock. So the order is global paging lock first, and format, and then L page. Always use this order. If you reverse order, you will deadlock and your program will hang. Questions? And read the source code for more information. And here are some questions you need to think about. That's it. Questions?
Not Korean, no questions.